So question number 3 is a physical chemistry question. So when this is regarding to some form of kinetics, so there is a reaction that is given, and they have given when 0.01 moles of a gas is used, and it is placed in 1 decimeter container and evacuated closed rigid container in the presence of small amount of solid catalyst at 227 degrees Celsius. It decomposes as shown below. So this reaction happens where A gas is decomposes to B gas and C gas. Okay. The concentration of A gas was measured over time, and the results are shown in the following graph. So you can understand what is actually happening with the time. So when the time goes on, the concentration of A is dropping down, which is accepted because A should consume because B and C are formed, right? So the concentration is decreasing. Taking the order and the rate constant of the reaction as A and K respectively, write the rate expression for the above reaction. So here our reactant is A. So we can write down our rate expression as rate is equal to OI the R is equal to the rate constant is given K, concentration of A to the power A. Everything is there. Okay, so this is the simplest way that you can write. Giving reasons determine the value of A. So now you need to determine A, which is the order with respect to A. Okay, so what do you see about the rate? The concentration of A is decreasing. So this, according to the rate law, this is the one form of rate expression. But also you can check the differential form to check whether what is actually happening with this A. For an example, let's take this point and this point and this point and this point, right? So I can write rate is equal to delta concentration of A over time. Since A is consuming here as a reactant, I can put a negative mark, negative sign. So my concentration difference, since this is 1 decimeter, the number of moles is going to equal to the concentration. So 0.01 minus 0.008 gives me like 0.002 over the time difference here is 500 seconds. This could be MOLDM minus 3, and this is second. So this is at this point. So now I'm going to calculate at this point. So the rate is 0.004 minus 0.002. That is a difference in concentration of A. So again, this is going to give me 0.002 M over the time difference is 500 seconds. Okay. So what I can see here, the rate at the beginning within first 500 seconds is same as the rate after 2000 seconds, in between 1500 to 2000. So the rate is same while the concentration of A is decreasing. So what is the meaning of it? Even though the concentration of A is decreasing, the rate is still same. So what is the meaning of it? Can someone tell me what is the meaning of it? Even though the concentration is decreasing, the rate is same. What does that mean? Can you think about something? So concentration is decreasing mean over time the concentration of A is changing, right? So even though you change the concentration of A here, there is no change in the rate equation, which you should understand. There is no concentration dependency of A in this particular reaction, because in our rate law, if you think the order with respect to A is 1, our rate should be rate constant time concentration of A to the power 1, or either it is 2 or either it is 3. If you think our rate is concentration depending upon A in this particular reaction. Okay. But here, according to the information that they have given to us, we see although the concentration of A is changing over time, the rate does not change. Rate is constant. The gradient is constant here. So if this is happening like this, there is no concentration dependence. So surely my rate should be equal to K times A to the power 0. So this is a zeroth order reaction. Otherwise, if A is either 1, 2, 2.5, 1.4 or anything, the rate should depend upon the concentration of A. But here we see, even though A is a reactant, when the concentration is changing, the rate is not changing because the gradient is not changing. So there is no concentration dependence. Therefore, the order with respect to A is 0. Okay. So giving reasons determine the value of A. So you can either show these two calculation and mention when the concentration of A decreases, the rate does not decrease. Therefore, there is no concentration dependent of A to this particular reaction. Therefore, the order with respect to A should be 0. That is one form that you can explain. Otherwise, you can simply say the gradient or the slope of this curve gives the rate, which is not changing here. So there is no concentration dependent of A. So simple A should be 0. The order with respect to concentration of A is 0. Okay. So did you understand that explanation? That is important to know. I have two answers saying yes. What about others? Do you get that, or I need to explain it again? Okay, so you all agree, yes. Okay, so the idea is clear now. Okay, so you can write down as in two different ways. So our rate law now becomes just rate is equal to our rate constant. Okay, so that's the idea. So if A is equal to 0, A to the power 0 is 1. So rate is equal to rate constant. So that is what they are mentioning. Calculate the rate constant K. So according to our rate law, R is now equal to rate constant K. So my rate constant is directly equal to the rate. So you can just pick up these 2 points, either this one and this one, or the longest, either this one is this one. So I am not, normally I don't like the initial and the last point. So people normally try to get the diverse, but since you see the gradient is not changing, so you can use any point here. So you will use this reaction to this equation to show the rate. Okay, don't take closer points because normally we don't take closer points because we try to get the diverse, maximum diverse point. either this one and this one, or this one and this one, and then you subtract it and get the difference in time, and you can show the rate according to this equation. Okay, and this rate is equal to our rate constant. That is very simple. Okay. Next question. Calculate the pressure in the container when half of the initial amount of A gas has decomposed. Assume that the volume of the catalyst can be neglected. So according to our equation, so we have A gas here giving B gas plus C gas, right? So initially we used 0.01 moles. We did not have this one. So here they say final, the initial amount, half of the initial amount. So at the end of this reaction, there is 0.005 moles of this one, because 0.05 moles of this one is decomposed. So there will be 0.005 moles of B formed at this point, because stoichiometry is 1:1, and 0.005 moles of this is formed. Okay, because this becomes 0.001. 0.01 minus 0.005, which is the half of the initial amount is decomposed. So when you subtract this one, you will end up with this one. And the same amount that is reacted to is going to form here in B as well as C, which is the same amount. So you know the total number of moles is 0.015 moles now. Right? So this is the total number of moles in the system. So you know NT, right? And what else you know? You know the volume. You know volume. That is 1 decimeter, right? You know the temperature. That is 227 degrees Celsius plus 273 in Kelvin. And you know R, which is 8.314 joule per mole per Kelvin, or 0.08321 atm liters per mole per Kelvin. So you know this one. So according to our ideal gas equation, PV is equal to nRT. The only thing that you don't know here is pressure. You know volume, you know number of moles, total number of moles, you know R, you know temperature. Okay, so this is normally a normal typical question that you need to find the pressure. In fact, the pressure in the container is the total pressure. Okay, so the first point is you identify the total number of moles, and then you apply PV is equal to nRT. So that is the simplest way to obtain this total pressure in the container, because according to this equation, all three are gases. So the pressure is exerted by all these three. Then after 50% decomposition of A, which is the half of the initial amount, so this amount of is remain, so total is 0.015. And then you know volume, temperature, and R, so you need to find pressure, that's all. Okay, so this becomes very straightforward, this question. Moving on, so B. In the presence of a solid catalyst, the gas X decompose according to the following chemical equation. So this is very similar to this one. The only difference is the elemental symbol and the stoichiometrics are different. So 1 mole of gas was gas X. Okay, so we use 1 mole of gas X introduced to an evacuated container. So the container is initially evacuated. There is not much in the, there is nothing in fact. The initial volume of the gas was measured to be V0. So we know the volume of this gas. It should be the volume of the container, in fact, because it's an evacuated container. The gas will spread all throughout the container. The reaction was initiated by introducing a small amount of catalyst. Okay. The volume of the catalyst is negligible, which is very important here. The rate constant of the catalyst reaction is K1. Okay. Then the order with respect to the X is B. The initial rate of the reaction was measured as R0. So everything is given. So when you measure the initial rate here, so initial rate R0 should be equal to the rate constant K1, right, times the initial concentration of X gas to the power B, right? So this should be our rate for the initial system, right? The pressure of the system was maintained at a constant value by allowing the container to expand. The temperature of the system also maintained at a constant. So the pressure and these things are maintained constant, but the volume is now increasing. So you can imagine like a piston where when it expands, the volume is increasing, but still the pressure is same, like a air pump that you use to blow air into your tires. So these are very common examples. Write an expression for R0 using the terms B, K1 and B0. So we have to use V0. We have used R0, B, K1. So instead of X gas, we have to put in terms of V0. So it becomes straightforward because we know R0 is equal to the rate constant K1 times concentration of X gas to the power B. However, since this is the initial rate, you can automatically write this one because they are using 1 mole of gas and the volume is given. So instead of this concentration gas, I can write 1.0 over V0 because that is the concentration of X gas. So my final equation becomes R0 equals K1 times 1 over V0 because the concentration is 1 mole over V0 to the power V. So this is my final equation, right? Then they say it was observed that the rate of the reaction was 0.25 R0. So the rate is decreased because initially it was R0 and now the rate is 0.25 R0 and the volume of the container was doubled. So which means here the new volume is 2V0. When 50% of the X gas was consumed, calculate the order B of the reaction. So 50% of gas is consumed means initially we had 1 mole. So 50% consumed mean how much now we have now. So this should be 0.5 moles. Right? So we can write down the rate at this point. So it is given the rate is 0.25 R0. This should be equal to the rate constant. Now, this is the important point. This rate constant cannot be changed when the volume is increased because the temperature is maintained at a constant value. So since the K1, the rate constant is depending upon the temperature and the type of the reaction. So same reaction is happening here. So K1 is same. But the difference here is the concentration is now 0.5 over the volume is now 2V0, not V0. And the order is simple B because order is also not going to change. So how can I find B here? I can use this equation 1 and equation 2 to find B here, right? So in fact, if I use the board here to so I have two equations. So one is R naught is equal to K1 times we use 1 mole over V naught to the power B. And they say when 50% is consumed, so it was 0.25 R naught, same rate constant, and there will be 0.5 moles now, and this is to V naught, and this is B. The same thing. So when you divide this, this will be 1 over 0.25. K1 is going to cancel out, and V naught is going to cancel out, right? So typically this will be yeah, so you can just write down these terms separately. For an example, 1 to the power B over V naught to the power B. For an example, just to show you the simplification very simply, so this will be 2 to the power B, V naught to the power B, and 0.5 to the power B. So these are going to cancel out. So automatically you can see 0.25 is 1 over 4. So 1 divided by 1 over 4 means 4 becomes on the top side. So this will be 2. So 1 to the power B, then 2 to the power B over 0.5, 0.5 being 1 over 4. 1 over 2, 1 over 2 means it becomes on the top side. So this becomes 4 into 4 to the power B. So B is equal to 1. This is our final answer. Okay. So this question is not hard, but you have to identify this point because you cannot use the description that is given in the last part to identify B, because you have to use the description that is given in the previous case. So they are coming to a certain order. First they tell find or write down an expression for the initial rate that we normally use every time when the concentration is 1 mole and the volume is V naught. Then they say when 50% is consumed, try to find the rate. So they have given the rate also. So you need to understand they have given the rate because you need to find B. Okay. So this doesn't come like by automatic. You have to just analyze the question and try to do. So there is an importance of trying to analyze the question very quickly. So we solve this and you can get B is equal to 1 as in the board. Okay. So this question is also not hard, right? So if you really know your chemical kinetics, you will not spend much time to do this one. In fact, okay. In fact, even these two questions, you see this paper is not hard, right?